Having completed our derivation of the spherical harmonics, which are the projections of the angular momentum state back on the position eigenstate, we're now ready to look at the Heisenberg Lie algebra with spin. We now are going to recall that the Heisenberg algebra for 3 dimensions has an order 7. Where do we get that? Well, we have 3 positions with the 3 momenta, are IH bar times delta Kj, where the positions commute with I, and the momenta commute with I. And I have written here the eigenvalue of I. We could replace this with a capital I without any problem right here. And that would give us the commutation rules among these 7 different objects. Naturally, the positions x1, 2, and 3 commute with each other, and the momenta p1, p2, and p3 all commute with one another. So the only non-commuting parts is with one of the x's with a p where they both have the same index, and therefore this Kronecker delta does not vanish. So this algebra has an order 7. We then proceeded to build an orbital angular momenta, Lij, in this form here, and found that this rotation algebra closed by itself, namely Li times Lj is IH bar times Lk, with Ij and k cyclic. We also found that the commutation rules between the L's and the X's and the P's were given by this form right here, which in fact defined all vectors that are going to be vectors, objects which are vectors, under the rotation group will have exactly the same commutator. And you'll recall that is such that xi and xj follow the indices I and j of the L's when we write x commutated with L in that particular order. And therefore the exact same form with the indices is obtained down here, or for any vector in fact. To be precise, the Lij is not in the Heisenberg Lie algebra, obviously because it contains nonlinear products. These are nonlinear, and therefore it does not exist. The Heisenberg Lie algebra itself are all of the linear combinations of the 3 x's, the 3 p's, and the I. So that would be a linear combination with 7 coefficients. And these are, of course, quadratic. It is, however, in something called the enveloping algebra. Formally, products such as xi-pj are not defined in the abstract algebra, but they can be defined using the matrix representations once you have a representation of that algebra. And that's because when you find the representation, you can take matrix products. And using those matrix products, one can then take commutators, and taking the commutators, one can then form new Lie algebras. Now these products are formed in this enveloping algebra of the products of matrices that act upon the representation space. Okay, let me say all of that once again. If I start out with the x, the p, and the I have 7 elements. And let's assume that I find a representation of this Lie algebra. That representation means that x, p, and I are represented as matrices, although they may be infinite dimensional and infinitely dense. Still, they're matrices, and being matrices, I can then take products of those matrices and form objects such as this. That entire algebraic structure is called the enveloping algebra of the original Lie algebra. And it consists of all possible products of all of the matrices that represent the elements of the original Lie algebra. We continue with the Heisenberg Lie algebra with spin. Now we formed the O3 by taking these products and made the definition of the angular momentum in classical mechanics, then abstracted from those classical definitions from the XPI algebra to let the O3 algebra exist on its own. Now, this is an important technique, as I've already mentioned before. We now return to join the XP and I algebra with this J algebra, the total angular momentum, into an algebra of order 7 with the commutation rules between X and J and P and J taken as the exact parallel as they were when we had the X and the P with the L, except now we replace the L with the J. Let me state that once again. We know what the commutation rules are between the X, the P, and the I. And we know what they are of all of these objects with the L's. We now replace the L commutator of these and the L commutator with themselves with the symbol J and say, let J represent angular momentum in a more general sense. And when we do that, we get a larger algebra. So we define this J that has those commutation rules as the total angular momentum operator. And we define L as before in terms of the X and P to be the orbital part of that angular momentum. We now define a new type of operator, the operator S, which is J minus the L, and one can easily show that SI with SJ is IH bar SK, exactly like the orbital angular momentum or the total angular momentum. So it behaves as exactly as an O3 algebra. And also, therefore, its representations will be like the O3 algebra. And we're going to define this S to be physically what we call the intrinsic angular momentum, or spin. Whereas L has eigenvalues that are restricted to integers because of the rotation of the wave function around must join with itself in an integral fashion. It turns out that these spin eigenvalues do not have to be integral and can be are allowed to have the half-integral values of the representation that we previously found. To remind you where we are, we're looking at the Heisenberg algebra, LieAlgebra with spin. That means that we have the following elements: 3 X's, 3 P's, capital I, so we have 7 of those, plus 3 more angular momentum operators, Jx, Jy, and Jz, giving us a total of 10 elements in this LieAlgebra. So this algebra we call the Heisenberg LieAlgebra with spin. It is now easy to show that we can form, as I mentioned last time, a new object, SI, which is the Ji minus the L, where L is defined in terms of the orbital angular momentum. It's then easy to show that the operator S with X and S with P both vanish. And since S with I vanishes, it follows that we get the commutators as before of SI and SJ being angular momenta, and we break the algebra therefore into 2 sets. If we want the representations of the X, P, and J algebra, we can equivalently find the representations of the X, P, and S algebra, because the L's are known, because that's orbital angular momenta in terms of the X and the P's. So, if a LieAlgebra contains 2 basis sets that each close among themselves as a LieAlgebra, and all commutators vanish between the 2 sets, then this LieAlgebra is called the direct product of the 2 LieAlgebras. And the representation of the whole are the outer products of the vector spaces of each one separately. Thus we have the X, P, I, and J LieAlgebra, which is 10-dimensional, is exactly the same as the X, P, I, and S LieAlgebra, which is a cross-product LieAlgebra, meaning that all of the S's commute with all of the X, P's, and I's. Therefore, this algebra here has the representations of the Heisenberg algebra, the eigenvalue of I, which is H bar, x1 eigenvalues y1, y2, and y3 for the position, or we could equivalently use the momenta, cross product with S and sigma, which are the eigenvalues of the Casimir operator and its z component for the angular momentum algebra. This structure provides us with a non-relativistic quantum theory which automatically contains particles that have any spin value. And we notice how naturally the spin value comes in. It's simply adjoined to our regular quantum theory. So whatever quantum theory we have, we can adjoin those states with any spin state. And we see, therefore, that our previous spin state was simply a spin of 0, where this was the trivial representation here. This is actually a very remarkable result, because what we have done here is, by using the algebras in this way and generalizing them through the enveloping algebra, we obtain a result that predicts an internal quantum number, namely the quantum number of spin. The quantum number of spin is predicted by the fact that the total algebra minus the orbital part of that algebra can contain something, namely the spin, which has a representation which can be non-trivial. And indeed we find that angular momenta is not, orbital angular momenta is not conserved by itself, but only the total orbital angular momenta, which consist of the orbital angular momenta coupled with, summed with the spin, exactly as we have in this equation right here. So J is equal to L plus S. The total angular momentum is the orbital plus the spin. This ability to derive an internal quantum number using Lie algebras is really quite remarkable. We see that we were able to move to a quantum mechanics that encompass spin very, very rapidly from the group theoretical or the Lie algebra point of view. We now have wave functions that are exactly like the wave functions in non-relativistic quantum theory when there's no spin, and we couple that with spin indices, and we know exactly how these objects transform under all of the transformations that we have. We know that we can represent those wave functions as eigenfunctions of orbital angular momentum, and if they also have intrinsic spin, the thing that is going to be conserved if there are no outside torques on the system will be exactly the total angular momenta that's orbital plus the total angular momentum that is intrinsic. We are now ready to move to the relativistic version of that same derivation. In order to do this, it becomes extremely important to treat both position and momenta as 4 vectors, as we are very familiar in relativity. But the jump to take position to a 4 component operator means that time becomes an operator on an equal footing with the 3 operators for position. This is not a theory that's without some types of difficulties, because time now has to be thought of as an operator. But we can proceed, and the way that we can proceed will lead us to a very fast method of understanding relativistic wave equations, relativistic invariants, the Poincare algebra, and the Lorentz algebra. So let us proceed and then talk about the difficulties later when we talk about the position operators. We are aware from our theory of relativity that space and time are commingled by the Lorentz transformations. And so it's obvious that if we're going to have operators representing x, y, and z, that to another observer, those operators are going to be mixing up with the time. So time must be an operator on an equal footing with the position. And these 4 operators, x0, x1, x2, and x3, will form a a contravariant vector when transforming under the Lorentz transformations as we've previously described. Likewise, the momenta taken to a new frame will be a Lorentz transform momenta from a previous frame, where the zeroth component of the momenta is interpreted as the energy divided by the speed of light, just like x naught is interpreted as c times t, the time. It follows that if time were just a number, then it would become mixed with the position operators, so all must be operators on an equal footing. The only way to generalize these commutation rules in a straightforward way from xi pj as delta ih bar delta ij is to take the time and energy operators and write them as ih bar also in a covariant way. That means that we will postulate that p mu with x nu is ih bar times g mu nu, where I, as before, has a continuum of eigenvalues, but in nature, it appears, selects only the eigenvalue where capital I is equal to h bar. These commutation rules give us 4 momenta, 4 position, and 1 operator which commutes with everything. This gives us a Lie algebra that has 4 and 4 is 8 or 9 elements as a relativistic Heisenberg algebra. The state of the system can be expanded in 2 ways. One way is we could expand it in terms of a momentum eigenspace, eigenvalues, in which case we would diagonalize h bar, k naught, k1, k2, and k3, and these are the eigenvalues of momenta. Now you'll recall that k naught is energy divided by c. Now rather than use k naught, which has a continuum from plus infinity to minus infinity, remember, we could use m, which was the square root of k naught squared minus k vector squared, and then rather than use k naught, we could use the mass, but we would lose the value of the sign of the energy. Thus, we must also replace that sign of the energy in using the mass in the following way. Rather than using k mu like this, we must use mass, sign of the energy, and k1, k2, and k3, which is a k vector. That's very important because otherwise, if we just represented the mass as taking the 4th component, we would lose this energy sign, epsilon of k naught. Upon thinking about that for a moment, we realize that we have obtained 2, quote, internal-like quantum numbers. One of these is the mass, which is the length of the 4 momenta, which is often known for a particle, and the other is the sign of the energy. The sign of the energy will be the thing that distinguishes matter from antimatter, or particle from antiparticle. And, of course, will be critically important later on. And as we know from Feynman's work in quantum theory, an antimatter can be considered as matter traveling backward in time, simply because we must have invariance with respect to a multiplication of position and momenta, and if we take a negative time, that a positive time with a negative energy, that's just like a positive energy and a negative time. We will find, in fact, that such a relativistic Heisenberg algebra works very well for one particle. And the reason is because we can use a proper time, so to speak, to do the mapping for the time evolution in an invariant way. However, for many particles, one does get into conflicts, and one ends up with many proper times, and this is not, there's no feasible dynamics that's known that can help one deal with a multiple time dynamic. However, the Lie algebra itself does have the correct representations, and its use will give us deep insight into the relativistic quantum theory, especially when we expand this to include the Lorentz group, or the Lorentz Lie algebra. Okay, so we now begin proceeding in a way that's very reminiscent, almost identical to the way we did it for the non-relativistic case. We have our relativistic Heisenberg-Lie algebra, which has 9 elements. We're now going to define a new object called the angular momentum 4 tensor. It is actually the orbital angular momentum 4 tensor because orbital angular momenta is that is defined in terms of the position of the momenta. This tensor will be defined as L mu nu, and now you'll notice we will not use any vector notation because the epsilon symbol does not give us a vector for the angular momentum in a theory of relativity. L mu nu is defined as x mu p nu minus x nu p mu. It's obvious that that generalizes for Lij to the old angular momentum tensor that we have been working with all along. And now we have new components when mu or nu are equal to 0, and those we will see generate the Lorentz transformations. It's straightforward, and I won't belabor the point by deriving the commutation rules of 2 of the L's. But L mu nu with L rho sigma has the commutation rule of minus IH bar G times L, G times L, G times L, and G times L. These L's got left out somehow. And one notices the way the indices are done. 2 of these are positive and 2 of these are negative with the negative sign out front. We have the mu rho as mu rho here, nu with mu, and so forth in a very symmetrical pattern. The pattern for the commutation rules for the position and the momenta with angular momenta follow these commutation rules with L written first and IH bar positive, where we'll notice that x mu and then x nu occurs exactly following the indices of the L, which occurs first here. Obviously, L mu nu is in the enveloping algebra of xp and I, and it also obviously contains O3 as the Lij. So the L mu nu is the homogeneous Lorentz-Lie algebra, and it'll be shown to generate the Lorentz transformations as well as all of the rotations. The complete derivation of the representations of the Lorentz-Lie algebra is very extensive and would really take us about a 1-semester course to do properly. And so we will only take the results and explore that in separate lectures. There are 2 methods for this analysis. One of these is much easier to follow, but it does not give complete results. We'll present that easier one later on after we present the complete presentation and solution, which is due to the Russian physicist Gelfand. In analogy with the non-relativistic case, we now form a Lie algebra with the elements x mu, p mu, I, and an object m mu nu, where m mu nu has exactly the commutation rules with itself and with the xp and I that the L mu nu does. We define this m mu nu as the total angular momentum 4 tensor. And we also define a tensor S mu nu as the intrinsic angular momentum 4 tensor by the equations S mu nu is equal to m mu nu minus L mu nu. We see that there's a perfect analogy here between what we're doing now and what we did before in the non-relativistic case. It's easy to verify that the S's commute with the X's, the S's commute with the P's. And therefore, the XPIM algebra breaks into a direct product of a relativistic Heisenberg algebra and an algebra S. This S algebra is the Lorentz-Lie algebra. And what this enables us to do is something incredibly powerful. It enables us to study all of the Lorentz representations over here and all of the Heisenberg or relativistic quantum theory over here, and join those two together by outer products and form a very rich structure that should give us the dynamics, at least within space and time, of all structures in relativistic quantum theory. And it